Welcome back to Hansen Theory. This is the final episode of this masterclass series. Everything you learned so far leads to this moment, scaling formulations from controlled laboratory conditions into unpredictable production reality. Many codings fail not because formulation logic is wrong, but because scaling is misunderstood. Lab success does not guarantee factory success. Minority-thinking engineers know that molecular interactions behave differently under production constraints. Let's begin with the core challenge. In the lab, you control temperature, shear, mixing order, batch size, and environment. In production, variability is unavoidable. Tank geometry changes flow patterns. Shear rates increase. Residence times vary. Evaporation behavior shifts. All of these factors change effective molecular interaction balance. Hansen theory allows you to predict these shifts before problems appear. First, batch size effects. As batch volume increases, mixing efficiency decreases. Local concentration gradients appear. Additives may not distribute uniformly. From a Hansen perspective, this creates localized RA distance variations. Some zones fall outside compatibility limits. This causes flocculation, viscosity drift, or phase separation. Minority-thinking engineers design formulations with interaction tolerance margins. They ensure red values remain safely below 1 even under imperfect mixing. Next, shear and mechanical energy input. High shear can temporarily disrupt hydrogen bonding networks. It can also change polymer chain orientation. Pigment surface adsorption layers may rearrange. If your formulation sits near stability thresholds, production shear can push it beyond compatibility limits. By modeling interaction sensitivity, engineers adjust additive systems and solvent blends to maintain stability under shear stress. Now consider temperature variation. Production facilities experience temperature fluctuations. Raw materials may enter at different temperatures. Processing heat can raise batch temperature. Temperature changes molecular mobility. Hydrogen bonding strength shifts. Solvent evaporation rates change. Hansen modeling allows prediction of temperature-dependent interaction shifts. Formulations are adjusted to remain stable across expected temperature ranges. Next, raw material variability. Different resin batches may have slight molecular weight variation. Pigment surface treatment may vary between suppliers. Solvent purity may differ. These variations alter Hansen coordinates subtly. Small shifts can accumulate into large performance changes. Minority-thinking engineers account for raw material tolerance by selecting formulation windows that remain stable despite parameter drift. Now, let's discuss process order. Order of addition matters. Adding pigment before solvent blending creates different interaction pathways than adding solvent first. Polymer hydration in waterborne systems depends heavily on sequence. Hansen theory explains this through transitional interaction states. Intermediate RA distances determine whether stable structures form or collapse. Production protocols are optimized to maintain favorable interaction sequences. Next, storage and logistics. Large-scale production requires storage stability. Time becomes a variable. Slow molecular rearrangements occur. Additive migration can happen. Sedimentation risks increase. Engineers evaluate long-term interaction stability using Hansen parameters. They design formulations that resist slow incompatibility drift. Now consider application equipment. Spray systems, rollers, curtain coaters, and electrostatic applicators all impose different stress patterns. They affect solvent evaporation and surface interaction dynamics. Minority-thinking engineers test interaction behavior under simulated application conditions. They adjust flow agents, wetting additives, and solvent profiles accordingly. Next, defect prevention strategy. Common production defects include orange peel, cratering, fish eyes, poor leveling, inconsistent gloss, adhesion failure. All of these trace back to interaction imbalance. By mapping production conditions into Hansen space, engineers predict which defects are likely and correct them before scale-up. Now, let's talk about economic optimization. Scaling is not only technical, it is financial. Raw material cost, solvent usage, energy consumption, and waste generation matter. Hansen-based formulation allows cost optimization by replacing expensive solvents with compatible alternatives, reducing additive overuse, and minimizing trial batches. Now, the mindset difference. Average engineers react after scale-up problems occur. Minority thinkers design formulations that are inherently robust. They do not aim for perfect lab performance only. They aim for stable industrial performance across variability. They use Hansen Theory to predict interaction behavior under production stress, design safety margins into formulations, reduce dependence on operator skill, increase batch-to-batch consistency, shorten scale-up timelines. This is what separates research experiments from manufacturing solutions. Now, let's summarize the full journey. You started with molecular forces. You learned Hansen space. You mastered RA distance and red number. You explored polymers, pigments, solvents, curing, additives, environment effects, modern coating systems, industrial troubleshooting, and now scaling. Together, these form a complete molecular engineering framework. Hansen Theory is not a formula. It is a way of thinking. It transforms coating formulation from guessing into prediction. If you adopt this mindset, you stop chasing problems. You start designing outcomes. This is how top formulation engineers operate. This is how high-performance coatings are built. This is how minority thinkers lead the industry forward. This concludes the Hansen Theory Masterclass series. But your application journey begins now. This is Hansen Theory.